part 2 of covalent bonding, we're going to look at structures a little bit more complicated. Not that much more, but a little bit more. So polyatomic ions. Polyatomic ions are just structures that are ions, so they've gained or lost extra electrons. And polyatomic just means more than 2 atoms. So we're going to look at structures that are at least 3 atoms. Now, again, ions. Talking about a structure that has gained or lost extra electrons. So here's the thing about polyatomic ions, that these are elements that are not going to share under their normal conditions, under the normal number of electrons that they have. They will share if extra electrons are added or removed. So what is a polyatomic ion? It is actually a structure that has covalent bonds within it, but needed extra electrons to make it stable, or lose electrons to make it stable. First of all, water. We drew water. That was a simple one. We did that in the first part of the section. Well, now if we tried to draw the Lewis structure for a hydrogen atom bonded to an oxygen atom, we'd say, okay, I could share once, share back and forth, and that one's good. The problem is that oxygen isn't stable yet because it doesn't have 8. So what do we have happen here? A hydrogen will not bond to an oxygen atom in a 1-to-1 ratio. If we look at H3O, we have 3 hydrogens bonding to an oxygen. We'll look at this comparison here, say, okay, again, I guess I can show the empty ones here. Say, well, this one will share here, that one will share back. Again, trying not to get too sloppy here with our drawings. This one will share there. This one will share back. So the 2 hydrogens are good. The oxygen is good, but the problem is this third hydrogen needs a third one to share, needs an electron to share back. So are those stable structures? Absolutely not. They're not stable structures. So how do we get 1 hydrogen to bond to 1 oxygen? Or how do we get 3 hydrogens to bond to 1 oxygen? Well, they're not going to form stable bonds as is. So what do they need? They need to have extra electrons added or taken away. So now, if we look at, well, let's draw the structure for OH minus. So OH minus, which by definition is called the hydroxide ion. Right? Shout out to Ohio State. I'll say OH. So in our stable structure here, oxygen has 6, needs 2. The hydrogen has 1, needs 1. We pair the electrons, share one back. It's good to go. We've got this oxygen that still needs an extra electron. So now what we're saying is, well, if an extra electron were made available, that extra electron would fill in that spot, and now that oxygen is stable. First question people have, well, where did the electron come from? Right now, my answer is, don't ask. Because we're not bonding hydroxides yet to something else. Here's the simple answer. It'll come from something like sodium, because what do we know about sodium atoms? They want to lose. But right now, all we're going to say is the only way this structure can be stable is if the 2 atoms share a pair of electrons between them. And then an extra electron is added beyond what it normally would have. Now, if we look at this structure, still have to keep in mind that oxygen now has 6 electrons it did not share. That extra 1, actually, oxygen keeps. So now that's our structure. If we count, okay, this is our double check. Oxygen started out with 6 electrons. Hydrogen has 1. And then we gain that extra electron from a sodium atom or wherever it maybe came from. So what do we have? Now we've got 8. How do we know our structure is accurate? Well, we've got 2 electrons there. We have 2 electrons there. We have 2 electrons there. That's 6. The line represents 2 more. It has a total of 8. The last thing when we draw Lewis structures for polyatomic ions, if the number of electrons has changed now that it has a charge, what we simply do is put a bracket around the diagram or the molecule, and then put the charge outside of that bracket. If we go back to the H3O, H3O is not going to work, but H3O plus will. So if we draw this out, hydrogen molecule or hydrogen atom, oxygen atom, hydrogen atom. So we said two of them will pair up, share back. Let's say I'll do this one, share, and share back. So I got two of them to stick, the third one won't. Now what we've got here is I've got to somehow get the third hydrogen to bond on and something lose an electron. Now, here's where you got some freedom. Which electron do I lose? We'll make it sort of easy for your structure. Right here, oxygen has 2 electrons. Well, what if instead of it had 2, what if it only had 1? So let's say that 1 electron took off. And now what we have is an opening in that spot. So if it has an opening, what can we now say? We can now say that hydrogen will share there if the oxygen shares back. Okay, and actually I sort of drew that to the wrong spot. I really should say that one shares to that opening, and this one shares back down there. So let me clean that up, because I didn't do a very good job with that at all. Here's the pair again. This one shares to that opening and shares back. This one shares to that opening and shares back. So let's clean that mess up. What do we have here? We have an oxygen in the middle sharing to 3 different hydrogens. Looking closely, that oxygen still has 2 electrons that it never shared. And this whole structure we put in brackets with a plus charge. Again, if we count this up, the oxygen had 6 electrons to start with. The 3 hydrogens each had 1. That's a total of 9. Odd numbers don't work in bonding, right? So what do? We lose 1 electron. We now have a total of 8. And if we count our structure, we have 2, 4, 6, 8. We have a Lewis structure that is correct. Again, the more of these you do, the easier they get. I don't expect you to necessarily look at that and figure that right off the bat. Okay? Here's what I want you to do. Because on the next page here, I've got 3 more that I want you to try to figure out. 2 of these will work out. 1 of them will not. And in all 3 of these examples, nitrogen is going to be the central atom. So what we're trying to do is show that nitrogen will be in the middle. Somehow the hydrogens, okay, have to bond to it. And that's what you're going to try and figure out. Again, 2 of these will work. 1 of these will not. The first 2, NH3 and NH4, do not have a charge. The last one, NH4, does have a +1 charge. So that means when you draw the structure, draw it with 1 less electron in the structure so that you can show how that's being arranged. Make sure you clean up your Lewis structure so it's nice and neat. So what I'll do is I'm going to pause this, and then you can write these down. And this is something also I want you to, when you get a chance to do these, I want you to show me what you've got in class, and then we can talk about any other issues that you may have had as you work through these. Okay, I'm going to do 2 more here. Again, just maybe one more step of involved molecules in terms of a little bit more difficulty. There's 4 of them listed, but the 2 in the middle here I've crossed off because they'll be part of what I want you to show me in class at some point. So we've got CO3 and then we've got PO4. CO3 2-, and then PO4 3-. Again, you might be wondering how do we know what goes in the center? How do we connect? Here's a simple rule. It's always the atom that's in the center, or the central atom, the majority of the time is the least electronegative. So you're never going to see oxygen in the middle, rarely see oxygen in the middle. You're not going to see fluorine in the middle. What do you tend to see? You tend to see the element that is the least electronegative, or even another way to say it, has the most openings for electrons. For example, what's carbon? Has 4, needs 4. You're going to see that in the center a lot. Oxygen, which has 6 and needs 2, you're not going to necessarily see that in the center. You're definitely not going to see hydrogen in the center very much because it's only got one spot to bond to. So there's a couple little simple ways to try and remember that. All right, so if we look at CO3 and we look at PO4, we draw these out. If we know carbon is in the center with the first one, and we got 3 oxygens that are somehow going to bond to it. Again, I'm just drawing them here nice and close. Now, you notice each oxygen has 2 spots where it has 1 and needs 1. Carbon has 4 spots where it has 1 and needs 1. We're going to realize that this is not going to work out naturally, so we have a 2 minus. So what that means is we're going to add 2 extra electrons wherever we need it to make the structure work. So let's just start off right off the bat. Shares 1 back and forth. Share 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 1 back and forth. So far, so good. Carbon's only got 1 more spot where it needs an electron, but each oxygen each has 1 more spot also, a total of 3. So our numbers aren't going to match up. We cannot share between the oxygens because we cannot get a triangle. So we're not sharing back and forth there. We're not sharing between those 2 oxygens. So here's what we got to remember. We got to get the carbon fixed. So let's fix the carbon. Let's say here we'll share there and share back. So now what you got to watch out for is this carbon and this oxygen actually shared 2 pairs. Okay, 2 pairs, double bond. The other 2 oxygens only shared 1 pair. Now, the oxygen's taken care of, this oxygen's taken care of, okay? This carbon's taken care of, but the 2 oxygens still do not have an octet. They don't have 8 electrons around it. They each need 1 more. Now, there's nothing else to share, and again, they're not going to share back and forth because we can't form a triangle here. So remember, the charge tells us a 2 minus. So what ends up happening is those 2, the only way this will bond together into a stable structure is if these 2 oxygen atoms each get an extra electron. Now, can they just magically get an extra electron? No, what happens is they get, those electrons get taken from or released from something else like a sodium atom, like a potassium atom. So all we're going to know is, well, this is the only way those 2 structures, this structure will form. So now let's clean up and get a final Lewis structure. We have the carbon in the middle. How you draw this is kind of up to you because remember, there's still 4 sides to a symbol. The carbon atom has a double bond with one of the oxygens. It has a single bond with the other 2 oxygens. Oops. So let's move this kind of out down here a little bit more out of the way. So there we see that. Now, this is where you've got to keep your drawings nice and neat. The carbon and the oxygen that shares a double bond. This oxygen still had 2 pairs that were never shared between the 2. So we still need to show those. The other 2 oxygens ended up having 6 electrons that it never shared with anything else. That includes that extra electron from the charge. So we show those. Now, where did the dots go? Remember, an atom has, a symbol has four sides to it. So there's our structure. Now, if we do this correctly, move it out of the way, the last thing we need to do is put a bracket around this structure and say it has a 2 minus charge. So that means that this structure has 2 more electrons than normally what a carbon and 3 oxygens would have. Let's double check. Carbons have 4 electrons. We have 3 oxygens that each have 6, plus the extra 2 electrons, for a total of 24. So let's count. We've got around the oxygen 2, 4, 6, 8, 10, 12, 14, 16. Okay, so 16 electrons not being shared. Then we've got our single bond 18, 20, 22, 24. So we've still got 24 electrons. That's good. Now, let's make sure every atom has 8. So it's still kind of a mess here. But let's move these out of the way. Okay. And now let's count how many are around each atom. This oxygen has 8 around it. 6 unshared, 2 shared. This oxygen has 8 around it. 6 shared, 2 unshared. The carbon has 8 around it. All 8 are being shared. The last oxygen has 4 being shared, but remember, it still has these 4 that are not shared. So we've kind of gone through our double check to make sure that our structure is realistic. Takes a little bit of time to draw these out, but again, how much you draw also depends on, what you need to figure out. All right, so let's do PO4. Phosphorus, 5 electrons, needs 3. We got oxygens, have 6, need 2. Oxygens have 6, need 2. Oxygens have 6, need 2. Oxygen has 6, needs 2. So just start picking here. Share and share back. Let's see here. Share and share back. And let's do a third one here. Share and share back. Now, 3 of the oxygens have been bonded to the phosphorus, and they each need 1 extra electron. The 4th oxygen hasn't been touched yet, so it still needs 2. And if we look at the phosphorus is stable because it's already has all it needs. Some would say, well, we're done. Well, no, not necessarily, because we're trying to actually make 4 oxygens bond. Well, here's where it's a little bit different in terms of the sharing. If we look here, this oxygen still needs 2 electrons. Well, everything we've been doing so far has been this sort of has 1, needs 1. This share and share back. Well, imagine you're sitting next to a person you're sitting next to. They've got a pen, you've got a pencil. You both need a pen and you both need a pencil. So you've got the pen, your partner has the pencil, you share back and forth. You have 1 and you need 1. You're sharing 2. Let's look at it a different way. Let's look at, on a particular day, you've got the pen and the pencil, and your partner didn't bring either. But you're being a nice person and you're sharing. So you're still sharing 2 back and forth. It just so happens they started with you. So you've got the pen and the pencil, but you're sharing both back and forth. It's still sharing 2. It's still sharing 1 pen and 1 pencil between the 2 of you. It's sort of like, well, how did it start? So now what we're going to look at is here. We've got the phosphorus is going to share 1 to that oxygen, share 1 to that oxygen. It's still just 1 pair. It just so happens they both started out with the phosphorus. So we've got that taken care of. The last thing, these 3 other oxygens that are each short 1. Well, we've got this 3 minus charge. So one's going to fill that spot, one's going to fill that spot, and one's going to fill that spot. Now, we got a mess that we've got to clean up. Again, hopefully you're drawing these somewhat neatly and organized. So we've got a phosphorus in the middle, and it's single bonded to every single oxygen. So we can at least do that so far. And I'll lower this a little bit more. Okay, so we've got that at least. Now let's look at the phosphorus. All of its electrons were used up. If we look at the oxygens, 1 pair, 2 pair, 3 pair. 1 pair, 2 pair, 3 pair. 1 pair, 2 pair, 3 pairs. So for 3 of the oxygens, they had 6 electrons that were never shared. So 3 pairs of dots. And again, make sure you draw them neat. The last oxygen, you got to just be careful here as you count. There are 3 electrons there that were never shared back to phosphorus, and there are 3 electrons there. So it has 6 also. So we just want to redraw those. Remember, the symbol has 4 sides to it. Right, so, final piece to the puzzle. Put brackets around it and say it has a 3 minus charge. So what are we saying here? We're saying that the phosphorus, it can bond with 4 oxygens. Does it have to? No, but it can. And if it does, we have to have 3 extra electrons in the structure. Can we make a phosphorus bond with just 3 oxygens and no extra electrons? Yeah, we can. But what we're showing here is how 4 could bond together. All right, the last little piece here, this kind of summarizes everything that we've been doing with electron dots. So what I want you to do is, we're not doing any of the orbital notation. Purely electron dots, and purely give me the final Lewis structure for each one of these 6. Whenever you get to this point, obviously I want you to do these and show me in class what you've got for these 6. If you can do these 6, then this pretty much covers everything that you need to know. Okay? There'll be one other piece here that I'm going to pause, and then we're pretty much done with this section. So if you want to copy these down, and you can work on them later, and then I'll come back with the last piece here. Okay, absolute last thing was section 2, and this is by far one of the longest videos that we'll ever talk about. What we're going to do here is, I want you to, in class, we're going to use some atomic model kits, in which we're actually going to put little atoms together and look at their shapes. So what you'll do is, you'll come to class, and I'll give you a box, and what I want you to do is, you're going to be putting actually carbon atoms with oxygen atoms, using little sticks to kind of act as bonds, and we're actually going to put some together and try to figure out how we could bond them from that aspect, rather than drawing the electrons out. So what I've got are 4 different examples that I want you to do. And when you do this, obviously you can come to class, ask me for these models, but these colors here really correspond to those atoms. And what you're going to find out is they have a certain number of holes in them that will correspond to how many atoms can be plugged into them. So what I want you to do is see if you can actually put those together and start to look at how they're shaped. What's the shape of the molecule? How are they arranged? And is everything straight and linear, or do things start to get twisted and bent? On the next screen here, you do have the answers, at least if you're drawing the electron dots, how they would be arranged. And you might figure out more once you've put them together what their shape is. So this is something I want you to do in class when you get to this point. You just got to ask me for the model kits, and you can start working on these. The last thing that you'll realize, and I'm just going to briefly mention this, they talk about bond lengths and bond energies again. It's a little bit on page 182, and then again some more on 187. So as we're looking at these structures, it will be important to look at bond length, bond energy, how close the atoms are, how far apart they are. And then the very, very last thing is resonance structure. And you really won't see this until you actually put the molecules together in a structure. But what we're going to look at is there can actually be different ways that we can arrange those atoms. Ozone is an example. Okay, there's 3 oxygen atoms. We actually can put the double bond in a different place. Same thing with sulfur trioxide. It's SO3, and there's actually 3 different ways we could draw the diagram. Is it really a different molecule? No, not really, but there is some unique properties that come out of resonance structures. And they talk about that in the section. So it's kind of a little thing. We will come back to this more in section 5, but at least it can be introduced now, and you can recognize that a structure might have resonance in it based upon how many atoms it has and what the bonds are. Okay? So this takes care of section 2. Again, a lot of different things in here. It's like putting a puzzle together. Hopefully, as you're doing a few of these, it gets a little bit easier, because it's definitely something that usually doesn't give people too much trouble once they've really worked through some examples. Right? Then the next thing we'll be looking at is ionic bonds and how those bond together. It'll be nice with those because it's a little bit less writing that's involved with those.